There we go. Hi, everybody. Welcome back to Chem 163 here. Let me just finish doing all the setup on my end here. We're going to continue with a cat. Is that what I heard? No. She was just leaving. We're going to continue with Chapter 16 today. I apologize if I sound a little congested. It's because I am. I have like a sinusy allergy thing, I guess, going on for today, so that's just going to be what I get to deal with, so I may have to mute frequently to like sneeze or cough or whatever, so. Nothing really new on the agenda down at the bottom, so still doing Lab 6 this week. Lab 3 is still due on Friday. No news is good news, I guess, yeah. So, when we left off, we were talking about potential and how... Oh goodness, sorry, there's a cat that suddenly appeared. No. You may not jump on my lap right now. We were talking about potential and how the difference in energy is measured in volts, and what a volt was. A volt is a joule per coulomb. And that different metals have a different propensity to pass electrons from one place to another. So for instance, on the screen here, if I were to pass an electron from zinc to copper, this is the energy per coulomb that we would get, 1.10 joules per coulomb, or 1.10 volts. If I use nickel instead, I get less, because nickel doesn't want to give its electron away as badly as zinc does. Now, what if I wanted to go in the other direction? If I was going to push an electron from, say, nickel to zinc here, like if my electron started here and I wanted to move it up there, I guess I'll just hit this button to show that. That would require me to put energy in there. And so the E cell that I would get for this reaction would actually be a negative number. Now, that tells us something interesting. So we know that thing for like delta G, delta S, all those things, that the sign dictates whether something is spontaneous or not. And that for delta G, it's weird because negative is spontaneous and positive is not. For E, a positive number is spontaneous, and a negative number is non-spontaneous. And there's going to be some equation later on that relates E and delta G, so that we can do thermodynamics with this, because of course there is, right? Alright. Now, if I do this reaction shown right here, where I have nickel giving its electrons to zinc, this would be my voltage. But if I were to reverse the reaction, then the voltage that we would see would just be this process right here. And this would be a positive number. So when you flip the reaction around, you flip the sign on E for that reaction. That's going to come in handy in just a little bit when we start trying to construct cells out of any two substances we want to on the standard reduction potential chart. All right. Now, this chart that I'm going to show you is a variation of the chart that's in Appendix L of your textbook, so let me actually load that up. The chart that I have is from the textbook that I taught out of before we changed to the OpenStax text. So there will be different numbers on this chart. In fact, it looks like there's a lot more on this chart. Oh yeah, there's a lot more. Okay. The issue that I have with the chart that I'm about to show you is that it's not arranged by potential, but is instead arranged alphabetically. And I don't feel that that's super useful. Excuse me, I had to cough there. But anyway, you can see that for all of these various reactions, and I can just scroll through them slowly here, all of these have a potential voltage difference. So for instance, if I take perchlorate and I reduce it by 2 electrons to chlorate and hydroxide, so I need water to do that, the voltage difference for that is 0.36 volts. I don't know where my cursor went. There it is. Yeah. And I could do that with anything I want to, really. So here's chromium 2. If I turn it into chromium metal, the potential for that is negative 0.9. So I had to actually put energy in to get chromium 2 to turn back into chromium metal. And so on and so forth. And there's tons of these. Now, there's one particularly important one that we care about. And I'm trying to find it. Am I just blind? Where is it? Oh, there it is right there. We're going to look at this particular reaction in just a second here. But you'll notice that its voltage is exactly 0. And there's a reason for that. It's because we chose that. We're going to define a very specific half reaction as a standard. And we're going to assign its voltage to be 0. And that electrode is called the standard hydrogen electrode, or She. And the reaction looks like this. If I take 2 protons and 2 electrons and I combine them together to make H2, the potential for that substance is 0. This is a definition. We have just said that this happens at this voltage. Now, does this process generate energy or consume it? Well, the answer is it doesn't really matter, because E for these reactions is going to be kind of like so I haven't taught 162 out of this textbook. I don't remember if they use delta E or delta U, but in thermodynamics, we talk about internal energy and how you can never know what its value is, but you can know what changes of it are. For this, it's more or less the same thing. We're just setting a benchmark here. If I get this much energy out, I'm calling it 0. Now, am I actually getting 0 energy out? No. But if I relate this to something else, I can figure out how much more or less energy that process gets me relative to this standard. And so that's why we have set it to 0. Now, what does the standard hydrogen electrode look like? Oops. There's supposed to be a picture here, isn't there? Hold on. That's very bizarre. Why is there a picture on this slide? Why is there this space here? And nobody will know. Okay. Anyway, it just says what we have already said. Let's suppose, though, that we're going to do this reaction. So I'm going to take electrons from zinc, and I'm going to add them to H plus to make H2 gas. So in other words, I'm going to oxidize my zinc, and I'm going to reduce this. So we've got that for my reduction. It's already balanced, so everything is good there. My oxidation would be zinc becomes zinc 2 plus and 2 electrons. And then those would cancel. And that's the overall reaction. So now I could create a battery where reduction occurs at the cathode. So this would be the cathode side. Oxidation occurs at the anode. This would be the minus side. And I could make a battery out of these things. All right, how do I measure the voltage here? Well, the voltage would be whatever these potentials were. We're going to write it like this. And I should put little circles here because we're doing all these at standard state. And then if I want to figure out what E cell for the entire thing is, we would write it like this: cathode minus anode. Now, there is a reason that we do it this way. And the reason for this is that all of the numbers that we're going to be putting in here are going to be reduction potentials. Now, reduction occurs at the cathode, so that checks out. That's great. But at the anode, we're not doing a reduction. We're doing an oxidation, right? So I have to look up what my answer would be as a reduction and then flip its sign to make it an oxidation. Or in other words, I can just put the numbers in here and subtract them. If I were to flip its sign, then I would be doing addition, right? But we've already taken care of that with the minus sign. So what we're going to do is we're going to look at our reduction potentials for the cathode and the anode, import those numbers in the equation, and then subtract them like this. So let's do some examples here. So the first one that we're going to do is we're going to say, well, okay, I'm reducing H2, and this is the She, so this means that this value is 0 volts. So whatever I measure as my voltage when I hook up the zinc and the hydrogen cells, the voltage that the voltmeter detects should just be equal to whatever the potential of the anode is with a negative in front of it. And so that looks like this. So on the left side here, I have the anode where my zinc is. And the electrons flow through in this direction through the voltmeter into the standard hydrogen electrode. This is what the standard hydrogen electrode looks like, by the way. So we've got hydrogen gas here. Its pressure is 1 atm. I've got H+, whose concentration is 1 molar. And then I've got zinc 2 with a concentration of 1 molar as well, and a solid zinc electrode. When I do this, the electrons flow through in the direction indicated. And the voltage that is shown on the screen is 0.76 volts. Now, how do I actually know that the voltage meter is running electrons through in this direction? And the answer is that the cords that you hook up to it have specific inputs. And the assumption is that if electrons go in the black input and come out the red input, you should get a positive number. If the electrons are actually going the opposite direction through the voltmeter, in other words, what was happening is the electrons are actually going this way, then what will end up happening on your voltmeter is the number it prints out will be negative instead. So your voltmeter that you're going to be given on Friday actually has this functionality built in. It will tell you which direction the electrons are going. They always flow from the anode to the cathode. The anode is going to be the black connector, and the cathode is going to be the red one. If for some reason those are flipped because maybe you hook them up to the wrong metals, like, oh, I put them on backwards, then the electrons will flow in the opposite direction that the voltmeter expects, and it will just print a negative number. Now, as shown for this, If this is the observed voltage, that means that E cell is that, and we know that E cell is cathode minus anode. And so that's going to be equal to 0 minus whatever anode is to equal this number. So this number must be negative 0.76. And remember, these numbers that are being used are reduction potentials. Is zinc being reduced here? Well, no, it's at the anode, right? It's being oxidized, right? So it doesn't want to accept electrons, it wants to give them away. So it makes sense that from the perspective of a reduction, it would have a negative number, right? It is not as willing to accept electrons as it is to give them away, relative to hydrogen, which we're setting as our base point as 0. So to summarize what we talked about in that previous reaction there, the more negative potential you have, the less likely it wants to be reduced. Things with negative potentials want to be oxidized. They want to give their electrons away. What that means is that if we're plotting potential energy on the y-axis here, and putting metals with higher and higher potential, higher and higher up on the scale, if we're measuring voltage, this top end is the most negative, and the bottom end is the most positive. Yeah, that's a little backwards in terms of like what we would imagine, because normally negative numbers go at the bottom and positive numbers go at the top. But in order to line up our voltage with potential, this is how we have to arrange the numbers. It's a construction or a model that isn't particularly compatible with how we normally interpret the number line. So we just have to get our brain around that. Now, E cell is going to be the difference between these, right? And so that would be whatever the final is minus the initial. 0 minus negative 0.76 is positive 0.76. All right, let's do a different example using copper. If I use copper, here, copper has a potential of positive 0.34. If I set up my battery so that it looks like this, where I have copper at the anode, and then I have the She at the cathode here. I don't know how to draw the She very well, so we're just going to write. We're going to just write it like this. So here's what my battery will look like. So here's copper. It's a solution. This is a solution. Here I've got copper 2+, salt bridge. I've got H+, and then H2. If I do this, it turns out that the electrons actually go in this direction, which means that these are actually not what we would imagine them to be, right? The reason that it goes in reverse is because the potential of copper is lower than that of the She. So what ends up happening is that for this reaction that we've drawn on the screen here, the potential voltage would be cathode minus anode. Well, the cathode is 0 because it's the She. So this is what we think the cathode is. But the anode is a positive number, which means that when I do cathode minus anode, I get a negative number. So as written, with electrons going in this direction, if I could tap the pen on the screen here, there we go. As written, this reaction is not spontaneous, and the reason for that is because the E cell we calculated is negative. The reverse reaction would instead be spontaneous, where we flip the cathode and the anode. Remember that when we're calculating E cell, it's all a matter of perspective. What have you assigned as the cathode, and what have you assigned as the anode? That's going to dictate the sign of your answer. If you accidentally flip these two, you flip the sign. And that may or may not represent what you intend. So be very mindful that you put the correct reaction at the correct terminal. Oops. So I'm just looking to see if there's anything else that we care about here. This is all stuff that I've said. Now again, we're writing these always as reductions. And because of that, when we write metals as reductions, most of our metals don't want to be reduced. Copper is kind of strange. It actually accepts electrons pretty readily, and the voltage for doing that is positive. Excuse me, but most metals don't want this. Zinc is pretty typical of most metals. Zinc wants to get rid of its electrons, so if you write it as a reduction where I'm giving it electrons, we get a negative E. So on this slide, we have a summary of what we've talked about calculating voltages. We're going to set our standard of 0 as the standard hydrogen electrode, which again is that. I should probably write aqueous here, but H plus has to be aqueous. If relative to the She, the half cell that we're looking at wants to undergo reduction more than the She, then its E cell will be positive. If the electrode has a tendency to give away its electrons as opposed to accept them, then its E cell will be negative relative to the She. And to figure out E cell for any pair of half cells, the formula is E cathode minus E anode. Positive E's are spontaneous, negatives are non-spontaneous. All right, let's do something. Oh, well, first I'll show you my chart. This is the chart that I'm used to. Oops, sorry, I thought that was to zoom in. So I like this chart personally because it sorts them by voltage. If you're trying to find a particular substance, that can be kind of annoying. But if you're trying to do something like, say, make the biggest voltage, or if you're trying to do something like, say, what will react with what, this chart is much more handy. And we're going to show that in some examples later on. Now again, things that have the highest positive voltage accept electrons the most. So up here we've got fluorine. We know that fluorine has a super high electronegativity. It has a very high Z effective, if you remember that from 161. Its electron affinity is very negative. It wants electrons. Give me the electrons now. So fluorine will just take them. Hooray! And the voltage you get for that is huge. Going down the list here, lithium is like, I hate electrons. I hate them so much. Please do not give me more. God damn it. And so if we give lithium ion an electron, Its voltage difference is -3. That's tremendous. That's a really big difference. Is that the biggest difference? I don't know. I'd have to look at this table because there are a lot more voltages on here. Potassium is almost as bad, right? Yeah, 2.92. Now, you might notice that, hey, wait a second, I've heard of a lithium-ion battery. Yeah, we put this as the anode. You put the lithium metal electrode as the anode. It gives away its electrons real quick, and for each electron you get out of there, relative to the Xi, is 3.04 joules per coulomb. Now, what would the best battery be? It'd be something between lithium and fluorine gas. You could probably imagine why we don't do that. Fluorine gas is extremely toxic. Also, this battery would probably explode the second you hooked it up. But if we could stabilize it and make it safe and not have to deal with a gas, you would have a voltage of like 5.87 for a single reaction. And that would be amazing. Now, if a question that's coming to your mind is, well, how do I get a 9-volt battery out of this? There's no combination that I can do cathode minus anode to get 9, right? And the answer is, well, if I have voltages for batteries and I string them together in sequence, or in series, I should say, you can sum their voltages together. So what happens in reality is that we have a bunch of 1.5 volt cells, and we just put them all in a line. You put 6 of those together and you get a 9-volt battery. All right, so let's do an example. Let's draw this battery, and let's calculate its voltage. So the first thing that we need to do, well, first thing we need to do is go over to this screen. But the first thing that we need to do is we need to figure out what's being reduced and what's being oxidized. You would think I had learned my lesson here. To start over here, to give myself space. Alright, so what's being reduced and what's being oxidized? Well, very clearly aluminum is being oxidized, so we know that this is happening. We can tell just by looking at the charge on aluminum. Sorry, my nose was super itchy there, and I just stopped what I was doing to scratch it. All right, so there's my oxidation. Let's do the reduction. So that's got to be the nitrate. And 4H plus. To make NO. And 2 water. All right, how many electrons got moved in this process here? So we're going to have to write our oxidation numbers here. So this is -2. There are 3 of them. So -2 times 3 is -6. The whole thing has to equal -1. So this has to be +5. Hydrogen is always +1. Oxygen is -2, so this nitrogen must be +2. And then +1 and -2 for hydrogen and oxygen. There's all of our redox numbers. So we can see that nitrogen went from a +5 oxidation number to a +2, which means that we have reduced it by 3 electrons. And that's convenient because that's how many we needed. All right, the next step is to go look these up in appendix L, whatever appendix this is. So let's find appendix L. And I'm going to need more space than that. OBS just disconnected. Is it still connected? Okay. Hold on just a second. If you can hear my voice, let me know. Everything seems to be working still. Okay. All right, so there's the aluminum one. Now we have to look up nitrate and H+. So that's probably down here under the letter N. Yeah, there it is. NO3 minus plus H... Wait, hold on. I want 4H+. There's a bunch of these, so you got to make sure you get the right one. There it is right there. So it's this one right here. So this is plus 0.957. Now, again, remember, even though that this is an oxidation, I'm just copying the number out of the book because we're going to take care of that with our formula. So if the screen is blurry, what you can do... let me see if I can show this here. You could fix that by going to the... Sorry, right? So right here on the video, if you click on this gear icon right here, and then you choose quality, set the quality to 1080p, and it'll fix itself. All right, I think we're done with this anyway, so. Let's just get that off the screen. All right, so the voltage of our cell is going to be cathode minus anode. So reduction occurs at the cathode, so we're going to put the cathode's value down, minus the anode's value. And when subtracting a negative, it becomes positive, so we just do that. And the voltage of this cell would be that, 2.619 volts. Then what we could do is we could draw the cell real quick. So we would say, okay, so here's my anode. Here's my cathode. I've got an electrode in here. Going to an electrode. And a solution, and a solution. And a salt bridge. And then we just need to label what's in there. So at the anode, we've got aluminum and aluminum 3+. So we'll put that over here at the anode. So this would be aluminum metal. And our solution would contain aluminum 3+. And then we have everything else on the other side here. So we would have nitrate. And we would also have H+. And I would need to have, like, some sort of, I don't know, some sort of container that has NO gas in it. And then our electrode, since none of these are metals, our electrode would have to be an inert solid, so platinum. And so then if we did this, our voltage would go in this direction. And the voltage would be this number. Now, something to note, whenever we use appendix L to get a number for a voltage, you don't ever want to multiply it. Remember that a voltage is the number of, I don't know why this isn't writing, joules per coulomb. If I feed 2 coulombs through that, the voltage doesn't change. I would just double the voltage when I use it for a calculation. Actually, what I should say is I don't double the voltage, I double the energy, because the coulombs would cancel out, right? So if you feed extra electrons through, the energy per electron remains constant. So the takeaway here is that if we're trying to balance like a half reaction, I have to multiply everything by 5 or 3 or whatever to make the electron counts balance out. Don't change your E. E is intensive. Later on, we're actually going to introduce this equation. And so when I want to change the number of moles of electrons, so like say instead of doing 1 mole of electrons, I'm doing 2, this will be where we do that. All right. So I want you to try making a battery out of this. So first of all, write out the half reactions for the reduction and the oxidation. Then look up the values, in Appendix L. If you don't have Appendix L handy or you just don't have the OpenStax textbook open, here's the link to Appendix L. And once you've got the voltage for this cell as written, type it in the chat. We'll go over the answers in about 4 or 5 minutes. You don't have to draw a battery if you don't want to, but you can if you'd like. One more minute, we'll go over the answers. All right, so let's go back over here. Oops, if I could click on it. All right, so we won't draw the battery for this one, but we will figure out which one's being reduced and which one's being oxidized. So lead is being reduced because it's going from lead 2+ to lead. So we would add 2 electrons to balance that out. We got chromium here. Chromium is being oxidized to that. And now I got to balance everything. So this becomes 3. This becomes 6. 3. And then 2, 2, 6. All right, so I'm going to go look up the reduction for Pb2+, which means I need this chart again. We'll put that back on the screen. Boop. So I need lead, HIJKLMNOP. That's palladium. There's lead. So E for this. Well, I shouldn't write E cell. E cell's the whole thing. Oh, excuse me. Sorry, I realize you can't hear me cough, and then suddenly I'm apologizing. So E for this is, I can't read this number, negative 0.1262? And then we got to look up chromium, but chromium's going to be, chromium 3+ turns into chromium metal. There it is. Did I scroll far enough? I did. Okay. So that's going to be negative 0.744. Oh no, they're both negative. What will we do? Well, we do cathode minus anode, which would be, so reduction occurs at the cathode, so that's this one, minus the anode. And I'm going to lose this digit here because of subtraction sig fig rules. So I get 0.1262 negative minus 0.744 negative. Boop. And there you go. All right, any questions, let me know. All right. Last thing we're going to do before we take our break, let's suppose that I give you 2 half reactions, and I say, make a battery. But I want the battery to actually work and not run backwards. So, looking at these, which one of these would be the cathode and which one would be the anode for a spontaneous reaction? Well, remember that the equation is this, right? And the anode, since we're subtracting the anode, whichever of your half cells is more negative, put it in the anode. And that makes sense, right? Because the more negative it is, the less it wants to be reduced. In other words, the more it wants to be oxidized. Therefore, at the anode, we want to put the negative number. That will get us a positive E cell, and so our battery will have a spontaneous reaction. So for this, here's what I would say. I would say that this is going to be my cathode. This is going to be my anode. And that this reaction would then be spontaneous, and then I could write it as such. Let's see what my slides are asking us to do for the question here. So, which direction would the current flow? So I would have to flip this guy around because this is going to be my anode. So the nickel one remains the same at the cathode. The anode, the manganese, I'm going to flip that around. And then the voltage for this should be... I'm just abbreviating there. So that would be negative 0.23 minus negative 1.18. Which looks like it's going to be positive 0.95. I mean, I guess I should check that. Okay, cool. All right. Let's hit clear on this. And then we'll just... we'll just print everything here. So this is, again, everything that we just said. The more negative of your electrodes is going to be the anode. And it's going to move the electrons to the other anode, or sorry, the other electrode, which is the cathode. All right, that behaves exactly like we predicted, so I'm going to give you one. So I've got tin and I've got iron. Which one will be the anode and which one will be the cathode? Tell me what the voltage will be, and then draw a picture of it. So I'll give you 5 minutes. We'll go over the answer. We'll take a break. My internet connection is apparently just, like, crap today, so I apologize if the video, like, freaked out for a second there. 1 more minute and we'll go over the answer. Alright. So... Oops. Sorry, let's go back over here. It just has the YouTube info window showing on the screen because I've been looking at that. That's not what I want to do. No, do not remove all of the things in the scene. OBS. Alright, so... which of these is going to be my anode? Well, it's the one that's more negative, so that's going to be the iron, right? So that means that I'm going to flip it around. And then for my other reaction, I'm going to leave it as is. So this E and it's not cell because it's not the whole thing. There we go. And then this E is negative 0.45. So E cell is cathode minus anode. So reduction is the cathode. So that's this. Minus oxidation occurs at the anode. There you go. So the voltage would be 0.60 volts. And if I was going to draw a picture of this, it would look like... So we got our electrode. Solution. Salt bridge. All right, this is the anode. This is the cathode. We said that iron was our anode, so that means that this must be an iron electrode. This would be a solution with iron 2+ in it. Over here, we have a solution of tin 4+ and tin 2+ in it. Our electrode isn't present in the tin equation, so this must be an inert electrode. The electrons will go in this direction. And the voltage would be positive 0.06. Or, sorry, positive 0.60. Getting my numbers flipped. Sorry about that. All right. We're going to take a break. And when we come back, we will do some more work with batteries. So, let me get the clock on the screen. Let me tell it I never want to update. I really should just update it so it stops telling me this. But all right, we will see you in about 10 minutes. Alright, so when we left off, we were working on this problem. And so we drew a picture of the terminals on the electrochemical cell that would make this reaction. And we calculated its voltage, and that's what we got. Everything is great. Alright. Now, if I gave you this reaction and I said no other information, and I just asked, is it spontaneous as written? How would we be able to answer that? So what we would have to do is we would have to calculate E cell, but notice that this problem says don't do that. Don't calculate E cell. So what we're going to do is first we're going to figure out what's oxidized and what's reduced. So let's write out the redox half reactions. So what is reduced? Well, that's magnesium. What's oxidized? That's iron. Alright, so this all checks out. Let's go look up the standard reduction potential for these things. So we got, let's see here. There's iron. I want iron 2. So iron 2 is negative 0. I can't read the number because it's so small. 447? Okay. Then we got to look for magnesium. Oh, shit. Hold on. Sorry. I scrolled on the wrong thing. Magnesium is, wow, it's negative 2.372. Alright. Remember, the more negative one needs to be at the anode. But what have we done? Uh-oh. So, our guess for this would be non-spontaneous. You can't see what I'm writing because this is in the way. There we go. So again, the more negative thing should be at the anode, but where did we put it? Uh-oh. So this reaction is non-spontaneous. The reverse reaction would be spontaneous. All right. So I have some more reactions here. For the first three, I want you to tell me, will the reaction as written be spontaneous or not spontaneous? So I'm going to number these. 1, 2, 3. And again, it's as written, so don't accidentally flip it on when you're writing it down. And then down at the bottom here, I have a solution that contains both sodium iodide and sodium bromide, which would oxidize only the iodide but not the bromide. Now, in order to do that, you're going to need the standard reduction potential table for both iodide, bromide, and each of these things. And so you're going to have to figure out which one will oxidize iodide, but then the oxidation of bromide would be non-spontaneous. So you might have to write a little bit out to figure out how to do that, but we'll go over that answer in just a little bit. So I'll give you about 5 minutes, 6 minutes or so, and then we'll go over the answers. One more minute, we'll go over the answers. Alright, so let's start looking up some of these. First, we gotta go over here. Oh, that was weird how that wiggled. Why is everything moving? Everything is moving away! I don't know why that happened. Why is everything selected? Why is everything ridiculous? There we go. Sometimes I just don't understand. Okay. So, for this first reaction, I want to write the reduction first. So, lead is being reduced. And iron is being oxidized. And if we go look up our standard electron or reduction potentials, HIJ, I went too far. So I get negative 0, or let's see here. Negative 0.1262. And for iron, that would be, oops, went too far. I gotta remember to get what I see on the screen on your screen. So, negative 0.447. Alright. So remember, we want the more negative one to be at the anode. So this one should be spontaneous. And it is. Great. Okay, let's do the second one. So, let's see here. What's being reduced? That is nickel. And then what's being oxidized? Well, it's the other thing, right? So that's zinc. Alright, let's get some E values. So what do we got here? So we got nickel, HIJKLMN. We're just going to do this. Negative 0.257. And then for zinc, QRSTVWXYZ. That's zirconium. There's zinc. Alright. More negative. Anode. Hooray. Excellent. Alright. I can already tell by looking at this one's not spontaneous because calcium does not want to do this. So what's being reduced? Yeah, calcium. You don't reduce calcium. Don't be ridiculous. What are we oxidizing? We're oxidizing zinc again. That was supposed to be an AQ. We'll just imagine it in our heart of hearts. So we already know this one, because that's from the previous reaction. I don't even want to know what calcium's is. It's going to be this ginormous positive number. Well, negative number, actually. Calcium. There it is. Negative 2.868. Yeah, that's not going to... Whap, whap. That's not going to happen. So, more negative needs to be at the anode. Oh, no. Non-spontaneous. Alright. How the heck do we do the fourth problem? Alright, so I have both sodium iodide and sodium bromide in my solution. So, I am trying to oxidize either of these things. So I'm going to write them both down. So these would be my oxidation reactions that occur with iodine and bromine. One of them is shown right there for bromine. Iodine has it's identical. There it is right there. I should have written down the voltages for these. So iodine is 0.5355. And then what was bromine? Bromine was 1.0. Is that an 8 or a 6? I can't tell. 8. Alright. Now, what we need to do is we need to pair something with this. To reduce it, right? If I'm going to reduce... Or not reduce it, we're going to oxidize iodine or bromine. Well, which one do we want oxidize? We want to oxidize iodine, but not bromine. Okay. So what we need is, remember, the more negative thing needs to go on the anode, right? So what that means is I need a number that is bigger than this. But if it's bigger than this one, that reaction will occur too. So I need a reduction reaction with E greater than 0.5355, but less than 1.0873. And the reason for that is because, remember, E cathode, which will be this number, minus E anode, which will be this number. If it's spontaneous, it's got to be a positive number. I want the oxidation of iodine to be a positive number, but I want the oxidation of bromine to be negative because I don't want the bromine to happen. So, let's look through the list of stuff that we have here. Let me do this so that we can just see the whole thing on the screen at once. And we're going to find stuff that has an E that is between 0.53 and 1.08. So let's start with chlorine. Will chlorine do the trick? Chlorine wants to be reduced, and its voltage is positive 1.35827. That's too big. That would reduce both, or that would oxidize both the iodine and the bromine. So that's not going to work. What about peroxide? Let's find peroxide. Actually, hold on while we're doing this. Too big. Oh, and I can also do this so we can see that. Alright, so now I gotta find peroxide. Did I get it on the screen there? I scrolled past it, didn't I? Alright. Peroxide can be reduced in the presence of acid to water, and its voltage is 1.776. That's too big. What about copper 2 chloride? So this would be copper 2 plus and Cl minus. Well, Cl minus can't be reduced further. It'd be Cl2 minus or something, so that's not going to work. But copper 2 could work. Let's find copper 2 on this chart. I just scrolled past it. So copper 2 being reduced to copper metal would be positive 0.34. That's not big enough. So that's no good either. Oops, I didn't mean to scroll to the next page. So, I mean, something obvious thing. It has to be nitric acid, right? So, nitric acid would be nitrate. And really, it could be any of these. But both of the top ones are approximately 0.95, is it? Yeah. And that would work, because that number is between 0.535 and 1.0873. So if I had a solution of iodide and bromide, and I wanted to get the iodide out of there by oxidizing it, I could put nitric acid in there. That would oxidize the iodide, but the bromide would stay that would remain as bromide. Now, this question didn't involve a battery. Huh? Can we do this stuff without batteries? Yeah, absolutely. A battery is just a mechanism by which we use the power of chemistry to extract useful work. But these reactions will happen on their own. Oops, sorry, that's the title card. Alright, let's do another few questions along that line of what will react with what. When we talked about acid-base chemistry earlier in the quarter, hey, remember those days? Doesn't it seem like it was so long ago? Not really, that was chapter 14, that was forever. We talked about how metals dissolve in acid. Now, the question we're going to address is, why does this happen? Why are metals so susceptible to acid? And the answer is, well, when metals react with acid, metals give up their electrons. And the acid, or two of these, can take the electrons. Look at what this is. It's the standard hydrogen electrode. So if a metal has a voltage for its oxidation, and all metals do, this is going to be my reduction. Here's my oxidation. I hate that they're backwards, but this is just what I did. Remember that the voltage for this needs to be more negative at the anode. So in other words, since the She is 0, any metal with E less than 0 will react with an acid. Because cathode minus anode would end up being 0 minus whatever negative number I put in there would then be a positive number and thus be spontaneous. So as long as you are picking a metal off of the standard reduction potential chart that has a negative E, it'll react with acid. So we could go back over here to this. We just look at all these metals, and all of the ones that have negative potentials will dissolve in acid. So starting at the top, we could see silver actually does not react with acid, which is interesting. Aluminum totally will. Americium totally will. Gold? No. Gold does not react with acid. And you might remember that when we talked about this in 161, when we talked about electronegativity, I said, yeah, the noble metals tend to be resistant to oxidation. They don't react. And that's that in practice. Barium totally reacts. Beryllium totally reacts. Calcium, absolutely. Cerium, yes. Cadmium, sure. And so almost all metals will do this. There's just a few noble metals that don't. Copper actually doesn't. Iron definitely does. Gadolinium definitely does. Gallium does. And so on and so forth. So most metals do react with acids. And it's because nearly all of them have negative E values for their standard reduction potential. So that's what these slides are going to walk through is, well, if I write out the reaction with acid here, I get this, and this part right here that I'm boxing in, that's the standard hydrogen electrode. And thus, any metal whose reduction potential is less than 0 will react with an acid. Now, there are other acids out there. And those acids can oxidize stuff as well based on whatever the anion is. So, for example, nitric acid, if I bring this back up there, not only does it have the standard hydrogen electrode, which is at 0 here, but nitric acid also has nitrate in it. And nitrate has a potential of 0.957. What would react with nitric acid? Well, anything whose standard reduction potential was less than that. So that would include more metals. So nitric acid is more capable of reducing things. In fact, if I go find like NO or something like that, I don't know if I'm prepared to answer this question because I don't actually know what the oxidizing species is in aqua regia, but there are things in here. So let me find platinum. Where's platinum on here? Platinum is a very positive E value. It does not want to give up its electrons, so it's very hard to oxidize platinum. In the laboratory when I was working, I would regularly make platinum mirrors. And what that means is that my substance would turn into platinum with a 0 charge, played out on the side of my tube as a mirror, and then my experiment was ruined. Well, in order to get my tube back, because the tubes were more expensive than the platinum, which is a very weird thing to say, I had to dissolve the platinum away. But in order to do that, it had to be soluble in an aqueous solution, which meant it had to have a charge. So you can see here that it's very hard to react stuff with platinum. Platinum will not dissolve in most metals, but there's in most acids. But there is an acid out there called aqua regia where you can add HCl to nitric acid and it will dissolve things like platinum and gold. If I could find the active species on this chart somewhere in aqua regia, we would probably see that its voltage was greater than 1.2 for its E. I just don't know what it is. I thought it was like NO something, but it's apparently not. Or it's just not in this chart, so. So, by using nitric acid as opposed to just regular old HCl or something like that, you can dissolve and react with metals that normally wouldn't react with just like HCl. So, this includes copper. Copper is reactive with nitric acid. If you've ever done this experiment where you dump like nitric acid on a penny and it makes a brown gas, and then the solution that's at the bottom is blue, and all you're left with is like nothing because the penny is dissolved. It's kind of cool. Alright, so let's do an example here. Here are a bunch of metals. Which of these will not react with sulfuric acid? Now, sulfuric acid is going to turn into two things. It's got my H pluses and it's got a sulfate. Can sulfate be oxidized? Let's see here. Or, I'm sorry, can sulfate be reduced? SO4? So, this does not show up on the chart of standard reduction potentials. I do not see sulfate in here anywhere. So we're going to ignore it. So this is the only species in here. So what are we going to be looking for? Well, my metals could potentially react with H+, and so this would be the She. And therefore, anything that has a voltage less than She, for its reduction potential, will be easily oxidized by the She. So let's go looking for those metals on the chart here. Let's not cover up everything. Let's do this. Actually, wait, hold on. Let's do the top of the chart, because then it's easier for me to find stuff. Alright, so we'll go all the way to the top here. Oops. So let's find aluminum. Will aluminum react with H+ here? Absolutely. Its voltage is negative 1.662, so this will. What about cadmium? Actually, silver is next on the list. Here's silver. Silver is positive 0.7996, so silver will not react with sulfuric acid. Cadmium. Let's find cadmium here. Negative 0.4030, so that'll work. And then what about sodium? Sodium is super negative, so sodium will absolutely react with this. Negative 2.71, so for sure. I just noticed that the question is asking us which of these will not react with it, so there's the answer. Make sure you're reading the question that's asked. I'm guilty of that too. Alright. I'm going to give you a list of metals here. Boop, there you go. And what I want you to do is I want you to tell me, will it react with HBr, nitric acid, both, or neither? Now, the first thing you're going to need to do is figure out, okay, well, which acid does what, and what's their E for these. And then remember that these have to be less, their E has to be less than the E for the acid. Because the acid is always getting reduced. The metals are getting oxidized. Now, when would you be in a situation where it would react with neither or both? Well, neither would mean, oh, it's above both of them. Both would be, oh, it's below both of them. So, what I want you to do is tell me which metals do what. Maybe like 6 or 7 minutes to play around with the standard reduction potential chart. And we'll go over the answers in just a little bit. Oh, we're going to run out of time here, because it's already 11:50. But we'll go over the answers. So first of all, let's fill in these voltages here. So HBr is H plus and Br minus. Only this one can be reduced, and that's the She. So E for the acid being reduced is 0. HNO3 has NO3 minus, which can be reduced, and we said that that was this. Was that negative 0.96? I forget. Let's see. Yeah, that's close enough. Okay. So we need to figure out what the E's of each of these metals are. So I'm going to just write these down. So silver has a reduction potential of 0.7996. Tin, oops, oh, sorry, hold on. Scrolling on the wrong screen here. Tin, SN, where is it? Negative 0.1375. And then gold, all the way at the top here. Positive 1.692. And then, oh goodness, sorry. I had to actually move the mouse before I put the scroll wheel. Copper is positive 0.34. Alright, so we need to have, this number needs to be less than the E of acid. So silver here is not less than the She, so HBr won't react with it. But HNO3 will, so silver reacts with nitric acid. Tin here is below both of these, so it reacts with both. Tin will be oxidized by both of these. Gold, on the other hand, is above both of these, so this does not react with either. And then 0.34 is between them, so this reacts with just nitric acid. In fact, interestingly, there are no metals that can react only with HBr, but not HNO3, because HBr is a lower potential. And if you react with HBr, you have to react with HNO3. Alright. So, those are the types of questions I'm going to be asking you on the quiz, and also exam number 2, which is coming up in 2 weeks. And we're going to stop here. We're going to do all the thermodynamics crap next week on Monday. And this is probably going to be the last day of Chapter 16, because these last few sections are just... These are just like trivia. So we're probably going to breeze through those and say, like, oh, this is a thing that... Like, this is what a fuel cell is. A fuel cell has hydrogen, and so on and so forth. We'll talk a little bit about electrolysis, because... it's interesting, but I'm not going to do any questions on it on the exam or anything like that. So, yeah. We'll probably finish up electrochem on Monday, and we'll start kinetics on either Monday or Wednesday. So, I do want to thank everybody for coming out to the lecture. Make sure that you get lab number 3 done by the deadline. And this week we are doing electrochem, which is lab number 6. We're not doing lab number 5. You may have gotten an announcement last night. I sent out another announcement going, oops, I didn't mean to do that. I was looking for the pre-lab for lab number 6, and it turns out there is none. So nothing is due before lab. Just make sure you read through the lab because it's confusing enough. That's all I got. Have a wonderful rest of your day. We'll see you in lab on Friday. Go out and enjoy the sun.